Topic of today's discussion is something called the maximum power transfer theorem, as you can see in the board. I am PRABRIT BONDOPADHYAY from the Department of Electrical Engineering from University of Engineering and Management, Jaipur. So, let us get into the topic. Any circuit, any electrical circuit can be, as we have discussed in your previous classes, any electrical circuit can be represented by an equivalent circuit, which is known as the Thevenin's equivalent circuit. Any based on a few conditions, if you try to analyze the whole thing, any circuit can be represented by a circuit just like this. This is something called the Thevenin's voltage source, this is something called the total internal resistance of the circuit, and this is the load resistance. Now, why we are discussing this? Today, we will try to set up a mental experiment. What kind of experiment is that? The experiment is very simple. We have set up a circuit like this, which has a power source, a resistance, that is the total internal resistance, and another resistance, that is the load. So, the topic of our experiment is to judge what amount of power is being supplied to this resistance RL. Now, from this, as you can easily see, if a current I is circulating through this circuit, the value of the current I will be equal to E by RL plus R in. That is the current which is being circulated throughout the circuit. Now, what amount of power is being dissipated in this circuit? The power is being dissipated in 2 points in the circuit, one in this resistance R in, second one in this resistance R L, and the power is completely supplied by this power source or voltage source E. Now, if this is the amount of current that is flowing through this circuit, the power that is being dissipated in this particular resistance R L, the load resistance or our point of interest, will be nothing but this squared into R L, right. Okay. Now, you may see this power is basically dependent on again these three things. One is the E, another one is the R L, the load resistance, and the third one is the total internal resistance. Now, for any circuit, rather for this circuit, this E, the voltage source, is a constant voltage source, it is not going to get varied. The total internal resistance is a resistance, or rather it is a property that is completely being described or defined by the circuit itself. All the circuit components have some kind of contribution towards creating the total internal resistance of the circuit. So, the remaining part is only the load resistance. Now, in our experiment, what we are going to do? We are going to vary the load resistance R L and check what is the value of the output power. Once we are done with the experiment, we get a graph like this. In this axis, the power dissipated in the load is shown as P L, and in this circuit the value of the variable load resistance is shown. So, as you can see, from the very beginning, at the very beginning the current is equal to 0. So, it starts from 0, the point 0, and as the current keeps on increasing with the change in the value of R, or rather the R L, the current starts increasing, sorry, the power starts increasing, and it increases up to a point called X. Once it reaches this point X, it gets the highest power supplied by the circuit, the load resistance. But what happens once it reaches reaches this point X, and what happens after that? After this point, again the power starts to get decayed. Now, what is the significance of this point x? The significance of this point x is that at this particular point, the resistance of the total circuit or the total internal resistance of the circuit shown from the open circuited load terminal is exactly equal to the value of the load resistance. Are you getting my point? So, that means whenever the value of the load resistance in a particular circuit is exactly equal to the value of the total internal resistance of the circuit, the load resistance is being supplied with the highest power. That is the topic of our discussion today. That is something called the maximum power transfer theorem. So, it states in case of a DC circuit, the load resistance is being supplied with the maximum power or the highest power when the value of the load resistance is exactly equal to the total internal resistance of the circuit seen from the open circuited load terminals. That is the significance of this point. This is the kind of expression you get once you are done with the differentiation. Now, in this expression, see, if we have to maximize or minimize a quantity, the method of doing that is nothing but you take a differentiation, you take a first differentiation and calculate or equate the value of that differentiation to 0, and the value that you get out of that whole manipulation, again you have to differentiate this whole expression for the second time, and you have to check by using that value that you have got in your first differentiation if this expression is giving you a positive value or a negative value. As it is conventional, if you get a negative value, you are going to get a maxima, and if it is a positive value, you are going to get a minima. So, as you can see, we have already differentiated this whole thing, and once we are done with the differentiation, we have to make this expression equal to 0. Now, in this expression, ETH cannot be equal to 0, neither this RTH plus RL. So, if we have to equate this expression to 0, we are going to get RTH plus RL whole square minus 2 RL into RTH plus RL equal to 0, because if the numerator has a value of 0 in this case, this problem does not make any sense. So, as this numerator cannot be equal to 0, neither this ETH square. So, only this remaining part can be equal to 0. So, let us see what happens when this expression RTH plus RL whole square minus 2 RL into this thing is equal to 0. What result do you get? This is the final expression. So, in this case, after a small mathematical manipulation, you can easily see as this and this both are not equal to 0. So, after taking a common, this whole expression becomes RTH plus RL minus 2 RL is equal to 0. From that, you will get this expression RTH is equal to RL. So, now it is mathematically proven that when the total internal resistance of a particular circuit becomes exactly equal to the resistance of the load or the load resistance, then the load resistance is going to draw maximum power from the circuit. And the value, now if we try to calculate the value of that particular maximum power, you have to replace this. If we replace this RTH by RL as RTH is equal to RL in this case, then the total power, then the total current becomes equal to E by 2 RL whole square into RL. So, that is nothing but E square by 4 RL. That is not the current, rather that is the power P max. I square into RL. Okay. So, that is the value of the maximum power that you may get out of any circuit, that is the value of E square divided by 4 RL, or in other word you may also write it as E square by 4 RTH, as the RL is equal to RTH in this circuitry. So, what does it tell you? It basically tells you that whenever the total internal resistance of the circuit becomes equal to the load resistance, then the power dissipated in the load resistance of any kind of circuitry becomes maximum, and that value of that maximum power, it is nothing but equal to E square by 4 RTH. As you can remember from the previous diagram that was representing the power versus resistance variation, the diagrams looked something like this. So, this point, at this point, the point at which the power becomes maximum, the relation is RL equal to RTH, and the value of the maximum power is equal to V square by 4 RTH. This is the point. Now, coming to the applications of this particular theorem, this has a huge application in case of circuit configuration. Why? What does it mean by this maximum power dissipation and thing? For example, any room has n number of points or n number of loads, and in these n number of points power is being dissipated, either they are being dissipated or they are being generated, either these are cells or these are resistances. I am just considering this circuit. So, either the power is being dissipated or the power is being generated. For example, in this case, in this E, the cell, in it the power is being generated, but in case of RL and RTH, in both the cases power is only being dissipated. Now, what happens in any circuit of our consideration, we have a particular point of interest. For example, in case of a very simple circuit which consists of a power source and a fan and the wires, in this very simple circuit there will be three components. One is the power source, second one is the fan, which is our point of interest, the load, and the third one are the wires. See, in the wires, every wire has got some kind of resistance, and as these wires have got resistance, power is constantly being dissipated in those wires also. So, some power, and we cannot take care, and neither we cannot use that power, right. So, the power that is actually is being used will be much less compared to the total power supplied to the circuit. That is the significance of this. For example, in many of the cases you have heard that the resistance of the microphone, the microphones that we use, if that resistance is somehow equal to the value of the resistance of the speaker, then the speaker gives the maximum output. In other words, the resistance of the amplifier when becomes equal to the resistance of the microphone, sorry, the speaker, then it becomes highest output. Why? Because this is the reason, maximum power transfer theorem. There are 2 points, there are 2 resistances are there, one is in the microphone and another one is in the speaker. Whenever these resistances become nearly equal or equal, the load resistance, or rather the speaker, can draw maximum power from the circuit itself, and that is why the need of impedance matching is there. There is another example is also there in the bikes or motorcycles. You will find that there is something called a starter motor. The effective resistance in case of those starter motors in scooters depend on basically 2 things. One is the resistance of the motor itself and the resistance of the cell or the battery that is supplying the whole power. So, whenever these two resistances become equal, that is called the impedance matching for the starter motor, and in those cases maximum power is being drawn to the starter motor itself. So, these are the basic applications of the maximum power transfer theorem. Also, you will find the application of maximum power transfer theorem in case of tuning of antennas. The same thing happens by tuning an antenna. Basically, the user tries to match the impedances of the source and the antenna. In this example, we will try to figure out what amount of maximum power that can be supplied to this particular resistance of 60 ohms, and to do that what amount, in this case what amount of maximum power can be supplied to this resistance RL. So, for the first thing is to open circuit the load resistance. I am doing that, and once we are done with the open circuiting portion, we have to find out three things. One is the ETH, another one is the RTH. In this case RL is already known to us. So, first let us start with the RTH one. To calculate the RTH, we need to remove the sources with their internal resistances, and in this case as it is a voltage source, you have short circuited the circuit. So, as you can see, if we look into the circuit from these these terminal, 40 and 20 are in parallel and this 60 is in series with the whole thing. So, the expression will look something like this: 60 plus 40 parallel 20. So, and it will be nothing but, so it will be around 73.3 ohms, around approximately. That will be the value of your total internal resistance. Now, if the total internal resistance is exactly equal to the load resistance, then the circuit is going to draw maximum power, and to calculate the value of maximum power we will be needing another parameter also, the ETH. How are you going to find out the ETH? For to do that, let us again place the voltage source in its position 120 volts, and we have to calculate what amount of voltage is coming at this open circuited terminal. And as this circuit is open circuited, this portion of this circuit is open circuited, no current is flowing through this, neither through this. So, we can also consider the voltage or potential at this particular point is exactly equal to the voltage of this open circuited terminal. Now, as you can see, this 120 volt is being divided among these two resistances, one is 40 ohms, second one is 20 ohms. So, if you just apply simple law of voltage division, you will see that 120 volt, from this 120 volt, 40 volt is being dropped at this particular resistance, and 80 volt is being dropped at this resistance, as the voltage drop in a series circuit is rather linearly proportional or directly proportional to the applied voltage. So, the VOC or the ETH in this case will be equal to 40 volts. Now, as we have already found out all the parameters to calculate the maximum power in this circuit, you can simply calculate the maximum power by applying this simple formula. That will be equal to 40 squared divided by 4 into 73.3. Thank you.